The whistle sounds at 6 a.m. Men pull on their boots in the dark. The boiler house is already hot. It is always hot. A low pressurized thunder running beneath the floor as steam builds inside iron walls that have not cooled in weeks. This is a working mill, a foundry, a factory floor where the machinery never sleeps, and the men move around it like blood through a body. The date is fixed. The place is fixed. 109 men will not go home today. It begins with a sound no one survives long enough to describe accurately. A crack, some will later say, those far enough away to survive. Then the building vanishes. The boiler, a vessel holding steam at pressures exceeding 150 pounds per square inch, fails in a fraction of a second. The metal does not bend. It does not leak. It detonates. The explosion tears through the structure at velocities that outrun human perception. Men standing at their stations have no time to turn, no time to step back, no time to understand what is happening to them. The force moves through brick and iron as though neither exists. What was a working facility seconds ago becomes a field of debris, steam, and silence, broken only by the sound of secondary collapses and, later, by the voices of men calling names that receive no answer. 109 dead. Dozens more injured. A community shattered in a moment measured in milliseconds. This is the story of why it happened, how it was allowed to happen, and why, across the decades of industrial history, it kept happening again and again. Before we understand the explosion, we must understand the world that built the boiler, and why that world decided the pressure was worth the risk. Steam power does not emerge from ambition alone. It emerges from necessity. By the mid to late industrial era, the economies of the United States, Britain, and continental Europe are running on thermal energy converted to mechanical force. Textile mills, flour mills, ironworks, rail yards, and manufacturing plants all depend on the same fundamental technology: heat water, generate steam, direct that pressure to drive pistons, shafts, and wheels. There is no alternative. Electricity is not yet scalable. Internal combustion is not yet reliable. Steam is the engine of the modern world, and the boiler is its beating heart. At the peak of industrial-era boiler usage in the United States alone, when more than 50,000 high-pressure steam boilers are in active operation, they power everything from riverboats carrying cotton down the Mississippi to the lumber mills of the Pacific Northwest to the steel foundries of Pennsylvania and Ohio. Demand is relentless. Production targets are set not by what is safe, but by what the market will absorb. A mill that produces more profits more. A boiler that runs hotter produces more. The economic logic is brutally simple, and it overrides every other consideration in facility after facility across the industrializing world. Workers understand, in a general way, that the machines around them are dangerous, but danger is normalized by necessity. A man with a family to feed does not refuse work because the boiler makes an unsettling sound. He learns to live with the sound. He is told by foremen, by owners, by the cultural consensus of his time, that the discomfort is the price of employment, that the noise means the machine is working, that the heat means production is underway. He is not told what the pressure gauge actually means or what happens when it climbs past its rated limit. If you are watching this and you work, or have ever worked, in an environment where the machinery around you seemed too loud, too hot, or too old, subscribe now. This channel documents the history that explains why those feelings matter. To understand why 109 men died, we must first understand the machine that killed them, what it was designed to do, how large it actually was, and why it could never be allowed to stop. A high-pressure industrial steam boiler of the late 19th or early 20th century is not a simple vessel. It is an engineered system of interconnected iron and steel cylinders, tubes, fireboxes, and pressure regulators designed to sustain controlled combustion at temperatures exceeding 300 degrees Fahrenheit, while maintaining internal steam pressure that, in working facilities of this era, routinely approaches or exceeds 150 to 200 pounds per square inch. To stand beside an operating boiler is to stand beside a contained explosion. The containment is the technology. The explosion is always present, waiting. The largest industrial boilers of this period are physically immense. Horizontal fire tube boilers, the most common type in foundries and mills, stretch 12 to 20 feet in length and 5 to 8 feet in diameter. The firebox at one end burns coal, wood, or oil continuously. Hot combustion gases pass through hundreds of iron tubes running through the water-filled shell, transferring heat. The steam collects in the upper portion of the shell and is piped out to the machinery it drives. Every component in this system operates under simultaneous thermal expansion, pressure load, and chemical stress. Every weld, every rivet, every seam is a potential failure point. The machine cannot be shut down between shifts. Cooling a large boiler from operating temperature to ambient takes 12 to 24 hours. Reheating it takes nearly as long. In a facility running on production quotas and hourly output targets, stopping the boiler is economically unthinkable. So it runs, day after day, week after week, in some facilities for months without a full inspection. The scale appears stable. The gauges read within normal range. From the outside, the building hums with productive purpose. Inside the iron walls, the metal is accumulating something invisible: fatigue. The boiler looks safe because it is designed to look safe. But beneath the gauges and the steady hum, a series of threats are building that no worker on the floor has the tools, the training, or the authority to address. The men who work nearest to industrial boilers are not ignorant. They know the machine. They know its sounds, its rhythms, its ordinary behavior, after months or years of daily proximity. A boilerman can tell by ear whether the draft is drawing correctly. He can feel through the soles of his boots whether vibration has changed. He develops an intuitive relationship with a machine that will, in a moment of catastrophic failure, provide no warning he can act upon. What he cannot detect is what is happening inside the metal itself. Hydrogen embrittlement occurs when atomic hydrogen penetrates iron and steel at the grain level, making the metal brittle without any visible surface change. Scale buildup, the calcium and mineral deposits left by untreated boiler water, insulates the firebox tubes from the water meant to cool them, causing localized overheating invisible from any external inspection point. Stress corrosion forms at rivet holes and weld seams, microscopic cracks widening with each pressure cycle. A boiler that has operated continuously for 3 months without shutdown may have interior surfaces that look adequate to an inspector with a flashlight and no testing equipment, but are structurally compromised at a level that makes catastrophic failure not a possibility, but a mathematical certainty. Foremen receive complaints. Workers report unusual sounds, unusual smells, the sharp sulfuric edge that sometimes precedes a seal failure. These reports move up the supervisory chain and, in facility after facility documented in this era, they stop. They are noted. They are attributed to inexperience, to overcaution, to the nervousness of younger workers unfamiliar with how these machines behave. Production continues. If you have ever reported a safety concern at work and watched it disappear into management silence, leave a comment below. You are not the first. What makes this tragedy not an accident but a pattern is the evidence that exists before the explosion. In other facilities, other states, on other countries, where the same machine, under the same pressures, had already given the same answer, the explosion that kills 109 workers does not occur in isolation. It occurs within a historical pattern of boiler catastrophes so consistent, so geographically widespread, and so thoroughly documented that ignorance is not a defensible position for any engineer, facility owner, or regulatory body operating in this era. The Sultana disaster of April 27, 1865, occurs on the Mississippi River when an overloaded steamboat's boilers explode near Memphis, Tennessee. The death toll is estimated between 1,100 and 1,800 people, the deadliest maritime disaster in American history, exceeding even the Titanic in lives lost. The cause? A boiler patched inadequately 3 days before departure, operated under pressure it can no longer sustain. The lessons available from the Sultana are specific, technical, and immediately applicable to every land-based boiler installation in the country. They are not applied. The Grover Shoe Factory explosion in Brockton, Massachusetts, occurs on March 20, 1905. A boiler failure beneath the building kills 58 workers and injures 150 more. Investigators find that the boiler has been operating beyond its rated pressure and that the safety valve, the one mechanical safeguard against overpressurization, has been manually wired open to prevent it from triggering during peak production runs. The safety valve is not a design failure. It is a deliberate human override, made not by a reckless worker, but by management logic. The valve interrupts production when it activates, so it is disabled. Each of these events is investigated. Each investigation produces findings. Each set of findings is filed, published in industry journals, presented at engineering society meetings, and then substantially ignored at the operational level. The same design choices persist. The same maintenance shortcuts persist. The same override decisions persist. What these earlier disasters also share with the event at the center of this documentary is geography. These facilities exist not as isolated industrial outposts, but at the center of living communities whose residents have no vote in the risk being imposed upon them. Industrial facilities of this era are not placed at a distance from human habitation. They are built where labor is available, where rail lines run, where river transport is accessible, which means they are built inside communities, adjacent to neighborhoods, or within walking distance of the homes of the workers they employ. The men who feed the boilers at 6 a.m. have walked from houses within a half-mile of the facility. Some live within sight of the smokestack. A mid-sized industrial facility of this period employs between 200 and 600 workers on rotating shifts, with the boiler house operating continuously around the clock. Shifts run 10 to 12 hours. Men cycle through 2 rotations, day and night, with minimal crossover time. The wages are not generous, but they are the wages available. In single-industry towns, there is no alternative employer. The mill is the economy. The foundry is the tax base. The factory is the reason the school exists, the reason the church was built, the reason the town incorporated. This economic reality creates a specific and coercive form of silence. But workers who raise safety concerns do not merely risk dismissal. They risk the loss of the only livelihood available to them and their families in the only economy their community offers. The company is not a distant abstraction. It is the neighbor's employer, the town council donor, the name on the building where the workers' Christmas party is held. Challenging its decisions requires a social and economic courage that the structure of the community systematically punishes. On the morning the boiler fails, these are the men inside the building. Men from these streets, from these families, working their assigned positions with no knowledge that the metal surrounding them has already passed its limit. At some point during the working shift, the exact minute disputed by later investigation, and the exact cause traced through metallurgical analysis to a specific failure point, the boiler shell ruptures. What follows occurs in intervals measurable only in fractions of a second, but the physics can be reconstructed. The rupture begins at a weakened seam, a corroded rivet line, or a section of shell thinned by internal scale deposit and thermal cycling. The breach is initially small, a split, a tear, but the pressure differential between the interior steam space and the ambient atmosphere is so extreme that the tear propagates across the metal faster than any mechanical response is possible. In a vessel holding steam at 150 pounds per square inch, a failure of 6 square inches of shell area releases energy equivalent to a significant explosive charge. This boiler is not 6 square inches. The rupture does not stop at 6 square inches. The steam flash, the instantaneous conversion of superheated pressurized water to vapor, expands at approximately 1,600 times the volume of the original liquid. This expansion occurs in milliseconds. The boiler shell, no longer a vessel, becomes a projectile. Iron fragments, weighing hundreds of pounds, travel at velocities comparable to artillery rounds. The building's structural supports, designed to carry vertical loads, offer no resistance to horizontal shockwave. The walls go outward. The roof goes up. Workers at adjacent stations, men who are not in the boiler room itself, men who are at lathes and furnaces and loading docks, are struck by masonry, by flying iron, by the pressure wave itself, which is sufficient at close range to cause fatal internal injury without any visible external wound. A worker in the boiler house at the moment of failure has no experience of the event. There is no sound he hears first, no flash he sees, no impact he registers. The physics of the failure move faster than the neural transmission of sensation. He is there, and then he is not. But the destruction does not end at the building's walls. The energy released by the explosion continues outward, and the men farthest from the epicenter are about to discover that distance is not protection. The explosion at the boiler house does not respect property lines. The pressure wave propagates outward from the rupture point in a radial pattern, diminishing with distance, but not disappearing. Structures within 100 feet of the boiler house experience near-total destruction. Brick walls collapse inward or outward depending on their orientation to the blast. Wooden structures within 200 feet ignite from the superheated steam and burning fuel ejected from the firebox. The largest fragments of the boiler shell, pieces of iron weighing 300 to 500 pounds, are recovered at distances exceeding 400 feet from the original site, embedded in walls, lodged in the ground, resting on rooftops of adjacent buildings. Workers who are outside the main facility at the moment of the explosion, men who have stepped out during the shift, workers in outbuildings, delivery personnel, are struck by debris they cannot see coming from a direction they are not watching. The shrapnel does not whistle or announce itself. It arrives. As secondary fires break out from ruptured fuel lines and scattered combustibles, the water system, fed by the same steam infrastructure that has just failed, is compromised. Early response efforts, neighbors, nearby workers, the first men to arrive from outside the blast radius, face a scene of such total destruction that the location of victims is not immediately clear. The structure that contained 109 men has, in a meaningful physical sense, ceased to exist as a defined space. Finding the dead requires searching rubble, not rooms. When the debris stops falling and the secondary fires are brought under control, the community begins the task that no community should ever have to perform: counting its dead. 109 confirmed dead. The number is both precise and incomplete. Precise because investigators and family members work through the lists methodically. employment records, shift schedules, the testimony of survivors about who was where on the floor. Incomplete because some of the dead are not recovered intact. The explosion and the fire and collapse that follow it reduce some of the men nearest the boiler to physical evidence rather than recoverable remains. Families wait for information about fathers, brothers, and sons with no certainty that there will be a body to bury. The demographics of the dead reflect the demographics of the labor force, men between 20 and 50 years of age predominantly, with representation from the youngest workers assigned to the most physically demanding positions in the boiler room and adjacent areas. Immigrants are well represented, as they are in nearly every industrial workforce of this period. Men who came to this country or this region specifically for this kind of work, who have not yet accumulated the seniority to hold positions farther from the machinery. The town stops. The mill stops, not by choice, but by the simple absence of a building to operate. The economic anchor of the community is gone, and the community does not yet know whether it is coming back. What it knows on the first night after the explosion is the list of names being read aloud in churches and meeting halls. Men who came to work that morning, who had nothing to do with the maintenance decisions or the pressure calculations or the override of the safety valve, and who are now dead. Within days of the explosion, the investigations begin, and the investigations will reveal, to those who read them carefully, that the question being asked is not the question that matters. Investigations into industrial boiler explosions in this era follow a consistent and, in retrospect, a revealing pattern. Engineers are appointed, metallurgical analysis is conducted. The failure point is identified with reasonable precision: a cracked seam, an overpressurized shell, a compromised safety mechanism. A report is written. The report is technically accurate and institutionally useless. The Sultana investigation in 1865 identifies the specific patch repair as the failure point and notes that it was approved under commercial pressure to meet a departure deadline. The systemic recommendation that boiler inspections be made mandatory and independent is not implemented federally for decades. The Brockton investigation in 1905 correctly identifies the disabled safety valve and notes that this practice was common across the industry. The facilities that read that finding do not, as a category, stop disabling their safety valves. The investigation into the explosion at the center of this documentary will follow the same template. It will identify a mechanical cause. It will correctly attribute contributing factors to maintenance deficiencies and operating pressure violations. It will, in its formal findings, stop precisely at the point where the findings would implicate the economic system that made the deficiencies and violations not just possible, but predictable. The boiler failed. The boiler was old. The boiler was improperly maintained. These are true statements. They are also incomplete statements that function. In the context of a formal investigation, as a mechanism for absorbing accountability without distributing it. The facility, or a successor facility under related ownership, will in many such cases resume operation within months. The same pressures will be applied to the replacement equipment from the first day it operates. The reason investigations consistently stop short of systemic accountability is not investigative incompetence. It is that the systemic causes are also the economic foundations of the communities and industries that commission the investigations. There is a calculation being made in facilities across the industrializing world, and it is not made by engineers. It is made by owners, by investors, by the men who set production quotas and approve maintenance budgets and decide whether to close a facility for an inspection that will cost 3 days of output. The calculation is this: the expected cost of a catastrophic failure, including investigation, compensation where legally required, rebuilding, and reputational damage, is lower than the ongoing cost of operating at the safety standards that would prevent it. This is not a secret calculation. It appears in industry correspondence. It is reflected in insurance actuarial tables of the period, which price boiler explosion coverage based on statistical failure rates and accepted the existence of those failure rates as a cost of doing business. It is reflected in the wages paid to boiler operators, wages that do not include any premium for the elevated mortality risk of the role, because the labor market of the period does not require such a premium. Workers need work. Work is available near boilers. The transaction is concluded. What makes this calculation morally catastrophic, and not merely economically rational from the perspective of those making it, is that the people whose deaths are being priced are not represented in the calculation. The worker who will die in the explosion has no input into the maintenance budget. He does not know the decision has been made. He does not know he is the denominator in someone's risk equation. He comes to work, he does his job, and he is killed by a decision made in an office he has never entered. Have you ever worked somewhere that made you feel like a line item rather than a person? Tell us in the comments. Yet the question this documentary must end with is not simply what happened in this explosion. It is what it took to change the system, how much it changed, and what the men who died in this building are still trying to tell us. Change comes. It comes slowly, unevenly, and under pressure, which is to say it comes in the same way that steam pressure builds, quietly, invisibly, until the accumulation can no longer be contained. The American Society of Mechanical Engineers establishes the Boiler and Pressure Vessel Code in 1914, driven in significant part by the accumulation of disasters documented in the decades before. States begin requiring licensed boiler inspectors. Insurance underwriters begin demanding documented inspection records as conditions of coverage. Yet the economics of the calculation begin to shift, not because owners become more humane, but because the cost of non-compliance begins to exceed the cost of compliance. Boiler explosion deaths in the United States fall from thousands per year in the early industrial era to dozens, and then to single digits across the 20th century. The technology improves, the oversight improves, the culture slowly, incompletely improves. This is real. It is the concrete result of the deaths of men, like those who died in this explosion, whose loss created the political and moral pressure that the industry alone would never have generated. But the architecture of the original failure, the prioritization of output over safety, the isolation of workers from the decisions that govern their risk, and the investigation process that identifies components rather than systems, that architecture is not unique to steam boilers. It appears wherever the cost of safety is borne by those with the least power to demand it, and the benefit of cutting that cost flows to those with the least exposure to the consequences. 109 men walked into a building on an ordinary morning. They did not know they were walking into a monument. They did not know that their deaths would be the argument that finally moved the institutions that their working lives could not. They deserved better than to be that argument. They deserved to go home. If this documentary mattered to you, share it with someone who should see it. Subscribe for more histories of the systems that shaped the world workers actually lived in. Oh, these stories do not end. But the men at their center deserve to be remembered by name, not only by number. The boiler is cold now. The building is gone. The names remain.